Service-level traffic variations, or protocol mutations, are deterministic variations in protocol state, structure, and semantics designed to expose weaknesses in protocol implementations and give engineers the information needed to correct them. These variations on normal application traffic can cause system crashes, buffer overflow events, memory corruption, and other abnormal service conditions that can lead to downtime or malicious exploitation. For most protocols, interoperability is based largely upon basic adherence to published standards. When dealing with more complex protocol interactions like those used in Voice over IP, IMS, and IPTV deployments, conformance testing is not enough to guarantee a high quality of experience. Vendors each have their own unique interpretation of the RFC they are trying to build from, and while they may fall within the literal confines of at least one version of the published specification, they frequently contain proprietary quirks that pose problems for vendor-neutral interoperability. An exception fault can be triggered by a protocol implementation not being able to properly handle unexpected variations in protocol traffic. Conformance testing assumes that the devices with which you will be communicating all adhere perfectly to the same published standards. While it is impossible to implement exception handlers for every possible contingency, solid input parsing and validation allows systems to gracefully discard those variants that are most likely to cause problems. A rigorous, automated, and repeatable program of negative testing can allow engineers to discover protocol implementation weaknesses and fix them before they lead to exception handling or interoperability problems. By measuring system responsiveness along a number of dimensions and correlating third-party information with attack states, the Muse Service Analyzer gives engineers an unprecedented level of visibility into the target's reliability, availability, and security. The Muse Service Analyzer generates millions of service-level traffic variations in a wide range of Voice over IP, IPTV, IMS, and other widely used application protocols. These variations embody a vast amount of knowledge gleaned through examining fundamental vulnerability patterns across protocols, by generalizing publicly known vulnerabilities, and using our internal security expertise. The dynamic service-level traffic mutations generated by the Muse Service Analyzer allow identification of previously unknown service weaknesses and vulnerabilities in a target application or device. Users can launch millions of mutations against a network to proactively expose weaknesses and take action to remediate them before these issues lead to costly downtime. CVSS base metrics are automatically generated to help project managers prioritize remediation activities. Since each target has a distinctive attack surface, surface configuration options like encryption, transport, and custom headers are adjusted for optimum protocol coverage. Service monitors, target recovery routines, and event actions like the collection of crash dump files can be captured and saved to a local XML template for later use. These templates can also be emailed and imported by other MU users to reproduce results or test other devices using the same settings. Variants represent a class of attack defined by a unique location in the protocol state model and a proven method of manipulation that will be used against the target. Attacks consist of thousands of individual attack vectors derived from the variant models, which vary patterns and lengths in order to evade static signature defenses. This is why these attacks are referred to as mutations. Service-specific instrumentation periodically checks on the health of one or more hosts, and this data is correlated with the attack sequence to establish causal relationships. A verification option is present at every stage of the analysis design phase to allow sanity checking against a live target. Transaction files, packet captures, and a built-in debugger allow the operator to fine-tune options and see the effects on the target in real time. Once we have ensured that the protocol model is tuned so that it can communicate normally with the target as a baseline, we are free to unleash millions of dynamically generated variations to exercise the input parsing and validation subroutines of the target. During the test, service instrumentation health checks are performed at intervals to gauge the responsiveness of the target along a number of protocol dimensions as well as SNMP statistics. Failure conditions are tied to either instrumentation failures where the target fails to respond to normal traffic within a variable timeout period, or other user-defined interactive monitor criteria. When a fault is detected, the target recovery routines bring the target back to its default state so that the test can be repeated to establish reproducibility before the test moves on. A confidence score is calculated for each fault along with CVSS-based metrics. Mutation patterns can be explored and studied using the embedded interactive protocol analyzer engine. Individual fields can be examined, and the semantics and structural elements are documented contextually. Common attack methods like buffer overflows and null strings are explained and can be viewed interactively in real time. I'll log into the Mu4000 interface and click on the Analysis tab to look at past results. Let's look at this SIP analysis, which has an SSH service monitor. On the Response Time tab, we can see the SIP and SSH response times, as well as red dots, which indicate where faults were detected. The timeline can be moved to focus on specific areas of the analysis. The rerun option allows us to use the results of this analysis to build a new analysis. Let's focus on just the variants that caused faults with a confidence level of 4 or higher. Now let's edit the analysis template to see how the test bed is configured. The Target tab contains information about how to return the target to an attackable state after failure, and the Attack section allows us to add or modify existing protocol mutations. Before we run the test, it is a good idea to verify the configuration to ensure that the Muse protocol configuration matches that of the target. When we get confirmation of green status, we can start the analysis. The analysis queue allows us to stack test jobs to execute in sequence. And the response time graph is built in real time during the test. Since we have an open SSH channel to the target, we can see the process activity of the SIP application being tested. These monitor results are captured by the Mu engine and appended to fault reports. The results of service-level traffic variation tests are presented in comprehensive reports which include engine logs, monitor data, and protocol transaction recordings. Vulnerability and availability statistics are collated into an executive summary providing business actionable intelligence to all project stakeholders. The service-level traffic variation module of the Mu Service Analyzer enables operators to uncover unknown vulnerability and performance-affecting bugs in a variety of common applications, including IMS, IPTV, and Voice over IP. Service instrumentation and SNMP-based monitors give engineers visibility into the unintended consequences of our proprietary variations in state, structure, and semantics. And deep protocol customization options allow a wide range of products and use cases to be tested in a systematic and repeatable way. Used in conjunction with denial of service modeling and published vulnerability attacks, protocol mutation testing helps ensure that service-affecting bugs are located, characterized, and addressed before they result in costly outages and downtime.